So according to the kind of data path that we have discussed in the processing unit, this is our pipeline stage organization with 4 stages. And here we have seen that there is chance for structural hazard because of the dependency on the hardware resource memory. Because while one instruction is reading data from the memory, there can be some another instruction trying to write data to the same memory. Also, while one instruction is being fetched from the memory, there can be some another instruction accessing the memory for reading the data or for writing the data. So now we shall see how in a MIPS pipeline processor, how the structural hazards are avoided by eliminating this kind of dependencies or by making the stages more independent and by properly organizing the stages of the pipeline. MIPS pipeline processor make use of a reduced instruction set, hence all the instructions are of simple addressing modes where each stage or each phase take one clock cycle and all the operations make use of only the register. The operations access the operands from the register and keep the result in the register. In order to interact with the memory, two separate instructions called load and store instructions are used. Only the load and store instructions interact with the memory and all other operations interact with only the registers. So here, in order to execute this instruction according to our old pipeline organization, in order to execute this instruction, we will fetch the instruction, decode the instruction, then load the operands from the memory locations B and C to the registers, to the processor register. Then using the arithmetic and logic unit, we will execute it and the result will be available in some processor register, and in the write stage we write that result to the memory location A. But here, using the load and store instruction, first of all the operands are made available in the register. Hence, both the operands B and C, the data from the memory locations B and C will be made available in the registers using the load instruction. So first, a load instruction, load the data from the memory location B to some register R0. Now another load instruction will load the data from the memory location C to some register R1. Now our basic operation add make use of only the register. It will load the operands from the registers. The operands are made available in the register. Those operands are accessed from the registers and the result is kept in another register. Now a separate store instruction is used to store that result from the register to the memory location A. So here we can see we are using more number of instructions, but even then we will get more benefit. Now with this kind of instruction set, our pipeline is organized into 5 stages. The first stage is the fetch stage. As usual, it will fetch the instruction from the memory. The next stage is the decode stage. Here the instruction is decoded and the operands are loaded, but the operands are loaded not from the memory but from the register because the operands will already be made available within the register using the load instructions. Hence, decode unit will load the operands from the registers to some buffer for execution. Next is the execute unit. It makes use of ALU to perform the ALU operations. And the result is written back to the registers at the write back unit. Here we are not writing it to the memory, we are writing the result to the register. So here we can see all the operations make use of only the registers, hence they will make use of these 4 stages. Instruction will be fetched, decoded, operands are loaded from the register, executed, and the result is also written back to the registers. Now to interact with the memory, we make use of a separate stage called memory stage. This stage will interact with the memory for data, both for reading data and also for writing data, and this stage will be used only by the load and store instructions. So let's see how it works. Our first instruction is loading the operand from the memory location B to the register R0. So in clock cycle 1, our first instruction I1 is fetched. And in the next clock cycle, this instruction moved to the decode stage. Here, this instruction will be decoded, and here we do not have any operand to be loaded from the register. So the instruction is just decoded. Also, in the execute unit, we have nothing to do. Suppose here we need to calculate the effective address of the operand. Then we need to make use of the execute stage. Here the execute stage is idle. Now in the memory stage, we will access the data from the memory location B. So the memory stage is used by the load instruction to load the data from the memory. But it is written to our register R0 only in the write stage in the next clock cycle. Now consider our second instruction I2 where the operand is accessed from the memory location C to the register R1. So in clock cycle 2, while instruction I1 is in the decode stage, the fetch unit can start fetching the instruction I2. So here the instruction I2 is fetched, and in the next clock cycle the instruction is decoded. Here also we do not have any operand to be loaded from the register. Here also we do not have anything to execute, no effective address calculation is required. But in the memory stage, we will access the memory to load the operand from the memory location C. And that operand is written to the register in the write back stage. Now consider our add instruction I3. So this is one of the basic operation which make use of only the register, and both the operands are made available within the register. So in clock 3 we can start fetching the instruction I3. In the next clock cycle, add instruction moves to the decode stage. Here the instruction I3 is decoded and both the operands are loaded from the registers R0 and R1. Thus here both the operands are made available within the register. That's why the decode stage accesses the operand from the register. Now the execute stage make use of ALU to perform the arithmetic operation. And here we are not making use of the memory stage. The memory stage is idle. The result of add is written to the register R2 in the write back stage. Thus, we can see the operation interact only with the registers, load the operand from the register, execute it. We are not making use of memory stage here. We are writing the result to the memory, and the next instruction will store that result to the memory and hence make use of the memory stage. Let's see how it works. The instruction is fetch. It is decoded, and here we need to load the operand from the register. The operand is available within the register R2. It will be loaded, and here we do not have anything to execute. Suppose if some effective address calculation is required here, then the execute stage is required. Here it is idle. And in the memory stage, here we are writing from the register to the memory. The store instruction also make use of the memory stage and access the memory to write the data. And this write back stage is not required here. We are not writing to any register. It will be idle. So, is there any chance for structural hazard due to the dependency on memory for data? Here there is dependency with respect to instruction and data. We will discuss it afterward. Do we have any chance for structural hazard due to the dependency based on the data? In the previous case, we were having two separate stages interacting with the memory for data. One stage for reading the data and another stage for writing the data. But here we are having a combined stage which will interact with the memory for either reading the data or for writing the data. And according to our instruction architecture, each phase take one clock cycle, and hence there will be only one instruction in one stage at a time, and that instruction will be accessing the memory for data either to read or to write. Here instruction I1 is accessing the memory for reading the data. At that time, there is no chance for any other instruction to be in the same stage accessing the memory for data. And here, while I2 is making use of the memory stage to read data, there is no chance for any other instruction accessing memory for reading or writing data. And here, while I4 is writing to the memory, there can be no instruction trying to read data from the memory. This is how in MIPS pipeline processor with a wise pipeline stage implementation, they have avoided the structural hazard caused by the dependency on memory with respect to data. But here we have one problem. Still, we have one dependency here. We have two stages which are dependent on the same memory resource. While one instruction is being fetched from the memory, at that time there can be some another instruction trying to read the data from the memory or trying to write the data from the memory. So we have discussed two ways of solving structural hazard. One way is pipeline stalling and the other is a proper organization of the stages within the pipeline. And the next solution is duplication of the resources. Here we can see the hazard is caused by one instruction is being fetched from the memory at the same time the data is being accessed by another instruction. So in one stage we are fetching the instruction, in another stage we are accessing the data. So if we can split the memory into two parts, instruction memory and the data memory, this problem can be resolved. So another way of solving structural hazard is resource duplication. Here also the dependency is removed, as a result hazard will never occur. And here we focused on memory, and the structural hazard can be caused by any hardware or resource. And in any case, resource duplication can be used if the cost is not an issue. And one other solution is pipelining the resources. For example, according to our data path, we have seen that in the fetch unit itself, we will update the program counter with the help of ALU. So while that is being executed, at the same time, suppose one another instruction is making use of the arithmetic and logic unit, then a structural hazard can occur. Here the dependency is on the arithmetic and logic unit. So here if we can pipeline our arithmetic and logic unit resource such that multiple operations can be executed in parallel fashion. So within the same clock cycle, more than one instruction can be allowed to use the ALU. This way, pipelining the resources, we can avoid the structural hazard, but here the complexity will increase. So first of all, to avoid the structural hazard, the pipeline stages should be wisely or cleverly organized. Even then, if there is some chance for structural hazard and if cost is not an issue, we can go for resource duplication. And also if complexity is not an issue, we can go for pipelining the resources. And after implementing all these solutions, even then the structural hazard, if there is some chance for structural hazard, then we can stall the pipeline. Hence, in only some cases, we may need to stall the pipeline and hence it will not much affect the performance of pipelining.